everybody. So back when we were studying groups, a couple of the big questions we asked were, first of all, what are some of the most important subsets of a group? And in that case, the first answer we gave was the subgroups. Those are some of the most important subsets. A second question we asked about groups a little bit later is if we look at their cosets, how can we give those cosets a group structure of their own? And remember, that led us to the idea of quotient groups, and we saw that we needed to make an assumption about a normal subgroup in order for that notion of a quotient group really to make sense. So what I want to tell you a little bit about today is at least give you a taste of how you study the analogous questions to those, but in the context of rings. So throughout this discussion, R is always going to be a commutative ring, and I want to tell you about a special type of subset of R, which is called an ideal. So namely, a subset I inside of R is called an ideal if the following two conditions are satisfied. First, if I take two elements, A and B, inside of I, and I add them, A plus B will still be inside of I. In other words, I should be closed under the operation of addition. How about under multiplication? Well, actually, I is going to be closed under multiplication, but it's even going to satisfy something a little bit stronger. Namely, the condition says that for every A and I, and for every B in the whole ring R, not necessarily in I, if I do A times B, it'll still be in I. The name people sometimes give to this property is that the ideal I absorbs under multiplication. The reason I use the word absorbs is that the way I think about what's happening is that the element A, which was inside of I, took something B, which might have been outside of I, and sort of pulled it in. By multiplying the two together, I wound up inside of I. Let me stress one more time that this means in particular that I is closed under multiplication, because if A and B were both in I, then A times B would be in I. But this is an even stronger condition than being closed under multiplication. So we're going to look at a bunch of examples of ideals in just a minute. Before we turn to those, I just want to motivate what we're doing by kind of telling you why ideals are a good thing to study. So first of all, I'm going to try to convince you throughout our remaining classes that ideals are something that show up naturally when studying rings. So in that sense, they almost play the role of subgroups, that they're kind of our favorite subsets of rings. And then the second thing I'll try to convince you of is that I can form a quotient, R mod I, which is the set of all left cosets of I in R under the operation of addition. And what I'll try to show you is that this only forms a ring if I is an ideal. This is analogous to the way in which a quotient group, that only forms a group if the thing you're quotienting by is normal. So in that sense, ideals are the ring theory version of normal subgroups in group theory. But okay, this is all getting a little bit ahead of ourselves. Let's look at some examples of ideals. For a specific example, let's let R be the ring Z of integers. And then an example of an ideal I would be what we've previously denoted by 3Z, meaning all multiples of 3. 0, 3, 6, 9, and so on, as well as the negatives. To check that this is an ideal, there's two things I should check. First, it should be closed under addition, meaning if you add two multiples of 3, then you'll get a multiple of 3. And that's true. If you wanted to write it out in more precise notation, you could say, well, if I add 3k to 3l, that's a multiple of 3 because it's 3 times the quantity k plus l. Then second, we need to check that I absorbs under multiplication, meaning that if I multiply a multiple of 3 by any integer in the world, I'll get a multiple of 3. And that's true. In notation, I could write that out by saying, if I take, let's say, 3k, that's my multiple of 3, I multiply it by anything at all, which I'll maybe call b, then the product of these two things is a multiple of 3, because it's 3 times the quantity k times b. That's one really important example of an ideal. Here's another one in a rather different ring. Let's let R be the ring R adjoined X. What this means, remember, is it's all polynomials where the coefficients can be any real numbers. Then inside of there, I'm going to let I be the set of polynomials whose constant term is 0. So for instance, I could take something like 3x plus 4x squared. That's an element of I because it has 0 constant term. The constant term, remember, is the one that has no x's in it. By contrast, something like, say, 5 plus 2x plus x squared is not in I because its constant term is 5 and not 0. To see that I is an ideal, it's helpful to think of it in a slightly different way. Another way to think of the elements of I are that they're the polynomials where I can factor an x out, right? Like notice here, 3x plus 4x squared, I could pull an x out of the whole thing. Compared to this other one, I can't pull an x out there. So what that tells me is that I is equivalently described as the set of all polynomials of the form x times something. I've written that as x times p of x, where p of x is any polynomial. When I write it that way, it becomes a lot easier to convince myself that it's an ideal. So first of all, it's closed under addition. If I took, let's say, x times p of x and added it to x times q of x, that would still be in I because I could write it as x times the sum of p of x and q of x together. Furthermore, I absorbs under multiplication because if I take something that looks like x times p of x and I multiply it by something else, any other polynomial b of x, then the result is still a multiple of x. Namely, it's x times p times b. So that's an example of an ideal inside of this ring R adjoined X of polynomials. Actually, staying inside of that same ring, we can find some great non-examples of ideals. Here's one. Inside of R adjoined X, let's let I be the set of all linear polynomials. What I mean by linear is that they should be of the form ax plus b, where a and b are any real numbers. In other words, they shouldn't have any x squared or x cubed or higher powers of x's appearing. So you can check that this is closed under plus. If I add two linear polynomials, I'll get a linear polynomial, but it doesn't absorb under times, which means that it's not an ideal. For instance, I could take the element 2x plus 1, which is inside of I could multiply it by a polynomial like, let's say, x. That's an element of my ring R. If this absorbed under times, then this should give me an element of I, but it doesn't. It gives me 2x squared plus x. That's got an x squared term in it, so it's not in I. So those are a few examples and non-examples of ideals. The last quick thing I want to mention before closing this video is what I advertised at the beginning, which is that ideals are really useful for forming quotient rings. Here's the statement of the theorem to that effect. So let R be any commutative ring, and let I inside of R be an ideal. And the statement is that if I look at the set R mod I, which by definition is the set of all left cosets of I under plus, meaning everything of the form A plus I, where A is whatever element of the ring, then that set, I claim, the set of left cosets, forms a ring. And what are the operations in that ring? Addition is what we're familiar with from thinking about ideals in the context of groups, namely the sum of the coset A plus I and B plus I is the coset A plus B plus I. And the multiplication operation is defined similarly. The product of A plus I and B plus I is the coset A times B plus I. So the name for this object R mod I is a quotient ring, just like the quotient groups that we've met before. So I'll leave it there for now. We'll get a little bit more practice with this concept in your worksheet for today's class. So I'll see you there.